So that this is overall our our application area, our world where we're standing right now currently. So these are the basic applications where we can focus. You know uh, starting from the aerospace to 5G communications, all are being covered by, being covered by the by photonics, right? So basically, just to give you the idea of the optical simulations, why we need the photonic simulations, or let's say optical simulations. So basically, that photonics and optical simulation can be classified into two parts. One is called optical simulation, or let's say a classical optic simulations, where we actually deal with the ray propagations of light, considering the photon, simply considering as a particle. And we think that only we consider that only photons is passing through some optical materials, optical geometries, for example lenses, mirrors, and all those things, all sort of things which are very very bigger compared to the wavelength of light itself. Okay. uh, but whereas in photonic simulation, the thing is quite reverse, quite opposite, where we actually think that the typical dimension of the of each and every component is very small, minute, I mean, which is very 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 close to the, it's comparable to the wavelength of light actually. So from here you can understand that it's typically in terms of nanometer or in terms of micron. Okay. So in that case, a lot of different things happens whenever we miniaturize our structure. Okay. So that the first thing which actually happened, that is surface to volume ratio changes, right? And it has a lot of applications in photonics. Okay. uh, so that's why, I mean, whenever we go to the nanoscale level, uh, the surface to volume ratio increases too much, and which can be exploited definitely for different applications. Okay, so now coming to the materials for photonics part, like that in photonics we use, I just like mentioned about the geometry, the device size. Uh, the one of the important part is assigning the material, which kind of material you are assigning. Okay. So okay, so now for the material part, as you can see, there are various type of materials we use for photonic simulation. So first thing is this metal. Okay, so that they have been exploited in traditional optics for centuries, primarily offering a flat or highly refractive surfaces. Okay. uh, uh, some noble materials, for example silver, gold, platinum, aluminum coatings are, they are very commercially available. Okay. uh, as you can see that where we can use the metals, okay, as a primary material. So first thing is that if we do want to design any kind of metamaterials substrate. Okay. As you can see in my slide, what are the typical dimension of this particular metamaterials or the meta surfaces. uh, it is below the operating wavelength. Okay, so basically it's typically a subwavelength structure. To create this kind of metamaterials, we can use metals. Okay, as a primary material, which has some special properties, for example the negative real permittivity, or the negative real permeability, and we can tune that by changing the geometry or changing the periodicity and all those things. We can definitely tune that as per our requirement, and we can come up with some novel uh, optical property of this particular design. Now coming to the semiconductors, instead semiconductors are of course ubiquitous in modern microelectronic devices. They possess band gap from zero point 0.2 electron volt to 5 electron volt. Okay. Silicon, of course, silicon germaniums, they are very very common. Gallium arsenides, indium and aluminum phosphides, all those semiconductor materials are available to design photo detectors or laser sources. Um, yeah, so basically it's also a kind of very important materials. Okay. For designing photonic components. Now let's coming back to the dielectric parts. Yes, we know that uh, dielectrics, a simple dielectrics, for example glass. Okay. This glass actually can be used, a most important component for both imaging and the non-imaging optics. It can be used for make lenses. Okay, right. uh, There are various type of glasses, even for for optical fiber. For example, if you auto design optical fiber, where you can use a various type of glasses, okay, calculated glasses or some basic counting glasses. All those things we use, for designing, for core material or the clad materials, right? Another application of the dielectric, is already I talk about this, glasses in fiber optics. Even we can use this PMMA as well, okay, right? So yeah, so that is one another material which comes under the dielectric. Now, conducting oxide, this category of this material are useful for like optical electronic devices, in which both good photon transparency and the electron conductivity are expected. For example, the front cover of solar cells and the displays are well-known examples. Uh, Indium tin oxides, or
Mm.
let's say aluminum zinc oxides, are the most studied materials, because they have a high transmission in visible and the near infrared wavelength. Coming to the nonlinear material, yes, several nonlinear materials we can simulate, we can design uh, as per our experiment, as per our simulation or as per our requirement. The lithium niobate, for example, to understand about the nonlinear effect of the lithium niobate, how to implement that material into in to create a electro-optic modulators, right? So we can definitely use that. We can try to understand the property of this lithium niobate. Then only we'll be able to design this kind of devices. And last but not the least is organic compound. I'll mostly focus on the organic compound today. Well, I'll discuss about the solar cell part. Yep, organic compound. It's organic compound itself a very right nowadays. It's a coming as a coming as I would say that it's a novel material while designing the solar cells, because it has some distinct properties. It's very much stable. It has long chain. It is very much stable, and it has some delocalized electrons. Okay, which can be used definitely for which can be used definitely to generate charge carriers, and definitely it has got a lot of applications in the solar cells. Okay, so now, so I would mostly focus on the solar cell today. So as you can say that, as you know that solar cell nowadays, we are using as a energy harvester. So there are different people are trying to increase a solar cell, the efficiency of solar cell by changing the material, by changing the geometry pattern. Uh, there are some couple of typical method we use, to increase the efficiency. The first thing is the trapping, the optical trapping, how to trap the photons, and how to efficiently get the absorption, okay, inside the active layer. Okay, that is our main agenda, and that's what people do in research, how to increase the absorption. So there are different techniques we can adopt just to increase the efficiency. So 3D pillar silicon cell, is one of them. We can create some kind of different nanowires to get the more absorption. Uh, then we can definitely, you can go for the tandem solar cell, by using material. For example, you can see that there is a several layers of the active material is built up of the gallium arsenide, and it is sandwiched between the two. It is a sandwich between one is n-doped aluminum gallium arsenide and p-doped aluminum gallium arsenide. Uh, so another thing is that the grating on the solar cell, uh, that we use a grating at top of a active layer, just to increase the absorption by simply increasing the reflectivity property of that grating. Okay, so it's another way of trapping the light. And uh, last but not the least is the solar cell type. Okay, so these are the basically type of solar cell which currently people use. uh, of course, solar cell is the newest one. And yeah, so I'll discuss about the solar cell a bit in the later sections. Um, Now, coming to I was talking about the materials. So these materials can be used for for bulk designs, or for a particle design, for a nanomaterial design, nanoparticle design. Sorry. Uh, these, the nanomaterials and the structures such as semiconductors, it can be made up of semiconductors. It could be made up of conducting polymers. It can. produce, for example, nanowires, carbon nanotubes, or silicon nanoparticles. It has a lot of applications, in different sectors. For example, designing biosensors, okay, we use nanoparticles, okay, gold nanoparticles, to exploit the surface and Raman scattering, to understand about the molecular property. Can somebody please turn off their mic? Still some noise is coming. Yeah, thanks. So yeah, so this particular, this nanoparticles is definitely can be useful for using for exploiting surface tenor Raman scattering, to know more about the molecular structure. The fluorescence microscopy, definitely we use nanoparticles. Then fullerene based structures is used mostly for solar cell design. uh, some inorganic based structures, for example, quantum dots, quantum dots also can be, can be generated from nitrogen vacancy, by creating some nitrogen vacancy centers. So it's a purely a inorganic based inorganic based substance. And it is very tightly confined, and these kind of, quantum dots basically used to generate a single photons. uh, and also some metal nanorods and metal nanoparticles. I was talking about this nanoparticles earlier about, while designing the biosensors. Uh, Similarly, so for example, if I talk about the metallic nanoparticles, we can use gold nanoparticles. Now, the gold nanoparticles can be used in several forms. Either it could be, form of a colloidal gold, okay, which is basically suspended into solution. The thing is that it has a strong absorption around 520 nanometers. These things actually we can simulate in our tool also, if once we know characterize a particular nanoparticle. These are, typical applications I was talking about the earlier.